Welcome everyone. Sorry we're a few minutes late, but just a pleasure to have Chongqing visit us. He's till recently was at Microsoft Redmond, and recently moved to a startup company called ByteDance, which does lots of interesting work. And if you look at his papers, it's kind of like the woo-zoo in data center networking, starting from DCell to DQ to server switch. Essentially, we could potentially fill a nice networking class with papers from which he has written. And more recently, he's been, before he moved, well, not quite recently, I think this was work that he did maybe 3 years back.
Yeah.
So he worked on RDMA networks and how to make RDMA networks work reasonably well. And that's primarily what he's going to be talking about today. And he's going to be back next Wednesday as well. So, he's going to talk about cloud availability in that seminar. Go ahead.
Yeah, thanks, Erwin. Yeah, I saw quite several very familiar faces here. Hi, guys. So thanks for inviting me to give this talk. I think this basically the RDMA work was started when I was in Microsoft Azure, then Microsoft Research Redmond. So I'm now in a company called ByteDance, and it's kind of more than a startup, but it's still not comparable to the big names. So it has several products. One of it is called Jinri Toutiao, or called Toutiao. It's a Chinese name. But because this product got so popular, so now the company is kind of called by its product. Now it's everyone in China called this company Toutiao. So this is basically the outline of the talk today. So if you have any questions to ask, I would like to, of course, very much to discuss with you around the talk. I'll be mainly focusing on the RDMA over commodities net. I think this is basically the future for RDMA, and I will put quite a lot of focus on kind of discuss what's next, right? So it's basically to make it kind of comparable to, for example, TCP/IP. So what do we need to do? So a little bit of advertisement for this company called Toutiao is kind of think it's a kind of AI-powered information and content platform. So if you think about that, is on one side is the content, and the other side is the content consumption, right? And so in the middle is the platform that we try to build, right? So this is a kind of more easy to understand. Is that okay? There are several parts. First is that this company is mainly a mobile internet company. It does not have apps on laptop at all. So everything is on the mobile internet. So it's the content and then the people, right? And use this. So you can see this is a mobile app, but behind that is basically the whole data center stuff, right? To provide all the intelligence. So it has a matrix of apps, right? But now currently mainly it's for the users are in China, but there are several parts. This is called Musical.ly. If you guys try, you can download that. It's just a company bought by our company. So we actually have a lab called the Toutiao Lab, AI Lab. So it's a very typical AI lab setup, and the people work on machine learning, computer vision, natural language processing. But I'm mainly working on the AI infrastructure and the cloud computing. That's basically what I'm currently working on. All right. So I think that's just a brief part of that. So what I'm going to talk about, basically the background is still cloud computing. I think about 11 years ago, when I tried to work on cloud computing, it was very hard to figure out what. At that time, actually, I didn't have an experience to go inside a data center to a big one, right? Of course, I got kind of a small ones, but for big ones, I really didn't get any experience. When I did the search on Google, right, you really could not find anything like that. But in 10 years, you can see, sounds like everyone is building a data center, right? And they are big ones, right? So I think this year, Microsoft probably will provide, in this year NSDI, Microsoft probably will provide the opportunity for the students and faculty members to go into the Quincy data center to take a look. So it's something like that, right? Very big warehouses, and the size probably is larger than a football field. And within the building, well, typically there's tens of thousands of computers there, racks by racks, thousands or even tens of thousands of these kind of racks, and they're connected. So basically, it's for example, Microsoft actually has more than 40 regions around the globe, right? That's a very big infrastructure. And so, of course, we build data centers to provide services, and but this talk is mainly focusing on a small part of the networking part, right? For networking, it's basically used to connect the servers together. I guess you guys are already very familiar with that, with the data center network structure, right? So it has some properties, right? Single ownership, very large scale, and also provide very high bandwidth network. Right? So basically, within the current reach of the networking, well, if you really want to pay the money, you can provide around 100 gigabit per second throughput between any two servers, and you can build this kind of structure for thousands of the servers, or even tens of thousands of servers, right? Big ones. So different from the high-performance computing community, we are doing this using the commodity parts, right? For networking, it's mainly the Ethernet switches, and using currently, I think 10 years ago, the Broadcom started to build commodity switching ASICs. So now, when we got even more companies building this commodity switching ASICs, right? So currently we have Broadcom, we have Barefoot, we have Innovium, and we have KVM, right? So basically, a lot of companies are trying to provide this kind of switching ASICs. And no matter what kind of switching ASICs they're using, a common character is that, okay, the communication protocol actually is TCP/IP based, okay. But the problem is that, I guess, I think everyone, even you are not in the computer science, you know TCP/IP to certain degree, right? So it's really not doing well. So this is a kind of a CDF figure. We try to measure the end-to-end latency provided by TCP/IP. This is provided by a project called PMesh, which I will talk about in the next week. So you can notice that basically the latency, even if you look at the 50 percentile latency, it's hundreds of microseconds, right? But that's but if you really look at that, right, basically the computers are within several typically it's 100 to 200 meters in the diameter. And that means that the propagation latency brought by should be just within microseconds level, right? But this is not what we are saying. So why is that? This mainly is because the software processing latency introduced by the OS stack. So because of this software processing, we got a very long latency tail there. And sometimes it can even reach hundreds of milliseconds. And next, if we look at the TCP processing overhead, well, So this is a very simple experiment. I think I did it probably 5 years ago, but it didn't change much. Right? Basically, if you run very simple experiment, you just ask the sender sending TCP/IP traffic to a receiver, and as fast as possible. If you're just using one TCP connection, you will not be able to saturate the network bandwidth. At that time, it was 40 gig. Now it is you can do it with 100 gig. And you will see basically the receiver will spend 4 to 5 cores just to process in the packet. At the sending side is a little bit better, so you will need 2 to 3 cores to process the packet. So why the sending side is a little bit better? It's because the sending side we can do this large segment of offload. It's basically you just pack up a big message into maybe I think it's 64 kilobytes. Then dump that into the NIC. Then the NIC will segment that into the packets and send it out. So that's save a lot of CPU cycles.
But the receiver side also has LRO, large the counterpart of the segment offload.
It turned out it didn't work that well. That's because you need to wait, because the receiving side is not that deterministic as the sending side. So you never know, who is coming. So basically, you wait for some time, then you kind of need to the packet delivered. And
so you are highlighting 12% utilization. The higher it's almost double. It's because the interrupt handling on the receive side. Why is it double the utilization on the receive side?
I think it's because it's still because of the difference between the sending side and the receiving side. Sending side has this kind of large segment of side offloading, and the receiving side does not have that.
Utilization on the server?
Yeah.
Oh, okay. I mean, receiving side is basically doing more work than the sending side.
The receiving side need to kind of I think the TCP/IP protocol is also more heavy at the receiving side.
Coding. I mean, like, just to figure out what packets are being received.
Okay. It's probably just not batching as well.
Probably, yeah, that's what it is.
Yeah, it's already doing the batching. Okay. But I think it's quite you probably can do a profiling. It's kind of quite easy to do and to figure out the difference.
So one question. So the setup here is VM to VM, or
it's physical servers.
Physical servers.
Yeah,
so it's just OS running on bare metal. Connecting. Okay,
that's right.
And it's sending large packets. It's not sending small packets, right?
Yeah, they are sending. If it's a small packets, the situation will be worse.
So even sending large packets, I would assume the bottleneck will be copying, but it's not.
It's not. The copy is just a small part of it.
And just as a, how much was the network component of it? Just like the median number you had was like 400 to 500 microseconds. The network delay component, was it in the order of up to 100 microseconds or something, or is it?
Yeah.
Okay.
Yeah. So basically, it's for Windows. Basically, the minimum network latency you can get is around 100 microsecond. If you're using Linux, it's a little bit better.
Okay.
Probably it's 70 to 80 microseconds, even if you don't do much. But varying the latency when the throughput is high is kind of a little tricky. It's because it got a lot of overhead from the server stack, and it can be sometimes it can be milliseconds. So that comes RDMA, right? Basically, RDMA is a kind of old technology, right? So it has been with us for quite a long time in HPC community, right? So it's basically you can consider RDMA as a overloading technology, right? So it's now because software is not good at handling packets. Why not just ask the hardware to do it for you, right? I think that's a very intuitive idea. So basically, RDMA was defined in this is basically that's InfiniBand IB InfiniBand association defined everything for RDMA. From the IB verbs to the layer 3, layer 2 protocols, even the layer 1 protocol. It's a kind of self-sustained. Basically you'll have everything from that. But today we are basically talking about RDMA over the Ethernet stuff. So why is that? Is it because InfiniBand, it's kind of specially designed for supercomputers, and but for data centers somehow because of I think the choice is mainly because we don't have other choices, right? So basically, the Ethernet protocol is the one that's been picked in data centers, and all the ecosystem is built on top of that. I think this is one reason. The second reason is that if you look at everything from the performance point of view, it does not have a difference compared with the InfiniBand. The throughput, the latency, right? And also the Ethernet has the ability to scale up very big, right? The biggest Ethernet data centers probably can be 10 times larger than the biggest data center built on top of InfiniBand. Okay, so this basically is how RDMA over Ethernet works. So it's essentially it's very simple, right? So this is the NIC, and you offload everything from the transport to from the transport to layer 3 to layer 2, all into the NIC, then you are done, right? But this is, if you compare with what TCP/IP protocol is located. So TCP/IP is here. It's basically the IP and the TCP, they are all in the kernel, right? So because of this offloading, you can see there's a big difference in terms of latency reduction, right? So RDMA typically can provide the understanding latency at a microsecond level. This is a big reduction compared to TCP/IP. And also, you can see the benefit of CPU overhead reduction. So CPU overhead reduction is that because now server does not need to do much, right? All this kind of protocol per packet level handling are kind of offloaded to a NIC. Then basically server it's kind of idle, right? It just need to do to process when the message is there. It just need to process the message. Yes.
Is the limit of RDMA latency the PCI Express latency?
Yes.
It's 1 microseconds because of PCA and nothing else, right?
That's not. So it's basically the 1 microsecond latency, 1 or 2 microsecond latency is kind of because part of it is because of the propagation delay. And also part of it is because when you need to do the transmission, you kind of need to have a transmission delay introduced by your bandwidth limitation. PCIe actually, typically it's not a bottleneck in the system, right? It can be faster than the Ethernet in most of the cases. So this is the measurement for 100 gig, right? For 100 gig, you can see just using RDMA, one single queue pair, we can have around the 9 rate. But this is not the case for TCP, right? If you have 100 gig NIC, right? If you run one single TCP/IP connection, the best throughput you get using Linux, you can get less than 20 gigabit per second. If you really want to stress the system, you can use multiple TCP/IP connections, right? No matter how many connections you use, the throughput is guaranteed to less, kind of a little bit around 50 gigabit per second, and it's not stable, right? Okay, so now let's talk about how to make how this RDMA over converged Ethernet works. Yep.
88 gigabits, not 100 gigabits.
And that's good port.
I see. So because of loss or?
Well, the good port is because the bare metal throughput is 100 gig. And this is yeah.
Okay. Is that the best we can do?
If you increase the MTU size, you actually can do a little bit better. You can increase that to around 92 gigabit per second. So that's the best you can do.
I also have a question about like the previous slides. So why TCP is only using 4.3 like the CPU? Is that like if you use more CPU, more cores?
Those are the total cores. We have 28 cores. Yeah.
If you use more cores, you can probably increase like the throughput of
It's I think this I think we can discuss this a little bit later when we come back to whether this is the software versus hardware trade-off. My guess is that this will be very hard so if you want to burn more cores, whether you can get a better throughput. I think definitely I didn't do any kind of optimization here, but I think that there's room there. But I have no answer how good you can, what's the best number you can get here. So we just saw the benefit. Let's see how we can have this RDMA work. Essentially, to make this RDMA work in an Ethernet environment, we kind of need two pieces of technologies. One is called this PFC, priority based flow control. This is for hop by hop flow control to make sure that. Oh, by the way, I didn't mention one requirement for RDMA is that for some reason, as RDMA needs a lossless network. So this is a fundamental different assumption compared with TCP/IP, right? TCP/IP is a best effort network, right? You can drop packets whenever you see a need, right? Congestion or packet got corrupt, right? But for RDMA, you cannot drop a packet because the network is congested. Well, you can still drop a packet if the packet is corrupted, but that's very small chance for that. But I think the bigger ask for RDMA is that it cannot drop packets. Right? Because of this, this PFC is just introduced for this purpose. So why RDMA needs a lossless network? I think this is for some historical reason. It's just bind together. Right, and I think one interesting research topic I think it's now ongoing is that how to do RDMA without the assumption. Right? I guess my guess is that there should be quite several groups are working on that.
There's actually there's a package drop. Your RDMA link just.
Yeah, we'll come back to that. I have some examples to show that. So this is one. The second is a protocol called DCQCN for connection level congestion control. So this is hop by hop. It does not differentiate flows, and this is something similar to TCP, right? It's to provide per connection level congestion control. So PFC is a kind of IEEE standard. So its idea is, I think its idea is very simple, right? So basically, well, you have two. So this is a connection. It's an egress port of the sending side, ingress port of the receiving side, right? At each side, you divide the traffic into 8 classes, right? Why is 8? I think this is just an arbitrary number because in IEEE Ethernet frames, it can only has 8 priorities. Okay, so once the ingress part is congested, kind of it will send back. So this is the frame format. It will send out a pulse frame to the sender to ask it to stop. Okay, it's very intuitive and simple, right? So its idea is it's basically the back pressure, right? If you cannot handle the packet, ask the sender to stop, and before you're sending out the pulse frame, you make sure that you have enough headrooms to absorb the upcoming packets, right? So it's a very simple and intuitive idea, and it's a very bad idea, right? So I think this is it's a place that to show us not all the simple ideas are good ideas. Right? This is a bad idea is because, in system design, we kind of have a principle is that, okay, you want to constrain your failures, or you kind of constrain your, when you are not doing well, you don't want to affect others. I think that's basically a principle that when you are building a system. But now, if you look at this pause frame, what it does is that if you cannot handle it, I will ask you to handle it. Right? This actually will cause a cascading, this kind of phenomenon, right? Right? Eventually, it will affect everyone. So we will see the cases later. So DCQCN is a protocol designed by us, so it's actually it's a good protocol. So the idea is very similar to what this kind of congestion control protocols are kind of asking, right? If you can basically there are several parts, right? Detection part and reaction part. So detection part is the switch congestion point, right? I think the idea in this protocol is actually is that okay, we try to leverage the existing mechanism to pick back the congestion signal. What we are doing is try to use the Ethernet. Basically, in Internet, we already have such a kind of detection mechanism. It's called the ECN, right? So once the switches detect the congestion, it will put a mark there, and it will let the packets go. And when packets goes to the receiving NIC, right? Receiving NIC notice that okay, this packet is marked, which means that somewhere in the network is congested. Then it will send back a notification to directly to the sending side, right? So in this case, it can kind of differentiate, which sending part is causing the congestion. So then the sending part can take action of that. So it's basically the idea is that okay, it uses ECN and plus some hardware-based congestion control mechanism to do that. And at the same time, it tries very hard to work with PFC, right? Because no congestion control protocol at the current stage can prevent packet from dropping, right? Because it's kind of unpredictable, right? So when the receiver will receive the packet, and when the sending side will receive the notification, congestion notification, right? So there will be a lot of uncertainty between that. But I think that what this case can do is that okay, it will try its best, right, to pass all those kind of information and react. So if there's a small chance that the packet may run after the NAC, you still have congestion, and this is the place that the PFC will be invoked. I think that's basically the design idea.
For this story, do you have to send long flows? Because essentially you're doing per connection is basically per flow feedback.
Yeah.
But if the flow is not long enough, then everybody is sending small packets.
Yeah. So if basically, I think that if everyone is doing this single packet flow, I think no congestion control will be able to work. If that's the case, I think the best chance you can do is that you can have a scheduler to do admission control. Yeah. So I think the assumption is that we still kind of have a mixed flow, and some are non-flows, some are short flows. But somehow the non-flows actually contribute to the majority part of the bandwidth.
Another question is, in this case, does it matter if you have very deep buffers or shallow buffers? So how does it affect how the congestion control the protocol level?
I think basically we don't want to have deep buffers because actually this will kind of delay the feedback signal of ECN. We just want to have a kind of reasonable buffers so that basically you don't lose packet. But at the same time, your kind of congestion signal can propagate in the network as fast as possible.
But this is different from TCP because in TCP,
No, TCP does not want to have
deep buffer.
deep
Because
buffer
you will
neither.
keep the buffer. But if you have ECN, and if you use PFC as a safety mechanism, safety net, right? If you use PFC, you will never lose packets. And then if you have a long queue, you're basically making yourself not to reach the point where you need the safety net.
I mean, the trade-off is that you have high latencies. That's the thing which you want to avoid. That is, queuing latencies.
Yeah, but I don't know how it works with RDMA because I know for TCP you have long queuing latencies because TCP tends to keep the buffer
Not if you
full.
use DC-TCP, right? So I mean, in some sense, DC-QCN kind of builds up on a little bit on the DC. I mean, it kind of builds on DC-TCP's insights.
But one of the arguments for this TCP is that if you use ECN rate, then you can have as big of a queue as you want, but you will never use up the whole queue.
It's still possible, like you can use the whole queue, like you use cheap pieces.
I mean, if your ECN mark is very low, if the threshold is very low, if your queue start building up, you're going to get 100% of your packets getting ECN mark. Then you will never actually take up too much of the queue, even though you have a lot of space left. So
No. I don't think that basically we want to use a lot of buffers, right? Because that actually will hurt our latency, right? But I think the ideal case that we are always struggling in networking is that we try to keep the buffer utilization as low as possible, but at the same time we want to keep the utilization reasonable, right? And the latency low. It's always a kind of try to keep that balance. But if we have to sacrifice, we want to have low latency. But we don't need to achieve 100% network utilization. But I think that's if we have to make the trade-off, I think that's the trade-off we want to make.
But here you want to prevent PFC getting used.
Yeah.
So if you have a big buffer, you will never use PFC.
But that's not our purpose.
Okay. You will have PFC deadlocks. So I don't know.
No.
Well, yeah. So I mean, the way to think of it is that I think the design philosophy is PFC can get used, but it should not get used often enough. That's really.
And I was asking if longer queue can prevent that.
From completely getting used.
Yeah.
Well, the other part of it is the engineering challenge, right? I mean, the switches have whatever, like 12 or 16 megabytes of buffer, and
Yes, I think the case is that we don't want to use big buffers, even if we can put. So currently, for economic reason, we don't have big buffers. But my argument is that even if we can afford that, we don't want to do that. So the thing is that we always want to prefer low latency than super high throughput. We want to keep the throughput reasonably good, like 80% or 90%. I think it's because if you are the designer of a network, even if the average utilization of a network is approaching 50%, you will ask for upgrade of the network. You don't want your network to be overly used for a lot of good reasons, right? And back to your question is that I think the thing is that we don't want to trigger PFC as frequently as possible, but for that we kind of just want to set up the buffers so that basically the ECN can be triggered earlier than PFC, right? And we always want to keep that threshold as small as possible, and we don't want to hurt the throughput too much. I think that's basically the trade-off we try to make. So after we design the protocols, we kind of thought, okay, we got the stuff there, and it should be working. But I think we were kind of just too optimal. Basically, that bad things could happen, but we didn't expect that. That's basically the rest. Actually, is basically the bad things that we run into. Some of them. The first thing we did. It was really a very simple experiment. So in this setup, we just it's the simplest setup, right? A sender and a receiver and a switch, and we are asking the sender to send a packet as fast as possible to the receiver using RDMA. And the one trick we play here is that we ask the switch to drop one packet over every 256 packets. Right? This trick is just to try to look at the ID protocol field of the IP packet, and if it's FF, I will drop you, right? Because the ID is kind of keep increasing, so I'm dropping 1 over 256. So I was expecting, okay, now throughput should be dropped a little bit, right? Because the drop rate actually is a little bit lower than 1%. Right? But what I got is a total surprise. So it's basically the throughput dropped to 0, but the good put dropped to 0. But if you look at the throughput at the switch side, it's 9 rate. At that time, it's 40 gigabit per second. It was quite a scary experience. And it was quite difficult to figure that out because it was 40 gigabit per second traffic. And capturing the packets was super painful. But anyway, I tried to manage to capture the packet trace and figure that out. It turned out things like that, right? Basically, I'm using RDMA send in this case. Basically, the message size is 4 megabytes. So it actually chopped into 4,000 packets and send it one by one. So what happened is that in every one packet got dropped in over 256, right? So after this packet got dropped, now the receiver will send back a NAK. That's a NAC, right? Basically, this protocol uses NAC. TCP does not use that. So then what the sender does is that, okay, it says a packet got dropped. Now what it does is it actually starts from the first packet and retransmit the whole message. Right? Because of this, it got into a nav lock because I'm dropping, in a kind of deterministic way, right? So then, in this way, it will keep sending, but without making any progress, right? So this protocol was built into the hardware, and it's in InfiniBand protocol for probably 20 years, or probably longer than that, right? And nobody noticed that. So at that time, I kind of got amazed. I think I kind of believed at that time the HPC guys probably are not as serious as we do. Because this kind of protocol, to my standard, it's not working. And so we work them, try to fix that. It's a little bit, because it's in hardware, we really could not do much. They provided a fix. Basically, this is the go back to 0, right? We ask them to do go back to N, to where the packets got dropped. You start from where your packet got dropped.
The RDMA standard is go back N, right? So they had a wrong implementation of the RDMA standard. Is that right? Or
they are arguing that it's a may, it's not a must.
Ah, got it.
Yeah.
Got it.
Okay.
So is it easier to implement go back to 0 or go back to N?
Well, of course, it's go back 0 is easier. you don't need to maintain any state. Right?
I see. So it's actually reduce state on the NIC.
Yeah. The second issue I'm describing here is kind of, I think this is the.
You talked to them and they fixed it, or did they?
Yeah.
They fixed it. Right.
You have to fix that.
Okay.
And also another question. So RDMA guarantees no drop, but I assume it doesn't guarantee ordering of packets.
No. Packets ordering has to be guaranteed in this connection-oriented. It's called RC.
Flow-based
Reliable connection.
Yeah. So if you do flow-led switching and so on, that will totally screw up RDMA because packets will be reordered.
So if RDMA sees a reordering or reorder that message, you also go back to 0 or go back to N.
Go back to N.
Yeah.
Okay.
Oh, well,
I mean,
it is supposed to.
Yeah. It cannot tolerate this reordering.
Okay.
Yeah. The second is even more scary. It's
a nice a paper on multipath RDMA in this year's NSTI.
Not from him.
Not but
From our interns.
from MSRA actually.
Oh, I see.
So
It's a very highly ranked paper, I think.
it might be the best paper. I think that makes sense.
So basically, this is this is also a real example. It's quite. I think at that time I was thinking. Of course, everyone knows that the deadlock may happen, right? Everyone knows that when deadlock happens, that it must be because you have some resources cyclic dependency, right? But in the beginning, I was thinking we could not have deadlock because our network is kind of this fat tree, and the routing is very simple. Packets go up, then go down, right? So for this up-down routing, there's no cyclic buffer dependency possible, so no deadlock. Theoretically guaranteed, no argument on that. But in reality, we actually run into a deadlock. It's a kind of very scary experience I ever experienced. Right? At that time, I've already worked on this project probably for 2 years. I spent a huge amount of time on that. Of course, as an engineer, I know that, okay, if you design something, actually it can deadlock. It means that it's useless. But for this case, the deadlock happened in a very clever way. So it's kind of a very interesting interaction with a very interesting feature provided by Ethernet. It's called this Ethernet broadcast. Everything is illegal. It's just you combine them together, it becomes illegal. Okay, let me see. Let me just try to walk you through this example. So this is a concept level Ethernet switch. So at the concept level, it has 2 tables, right? So it has an up table tries to translate IP address into a MAC address, and it also has a MAC table try to translate the MAC address into a port number. So it knows, when you receive a IP packet, which port it needs to send out by looking up those tables. So the thing is that, okay, now suppose you have a packet. You can look up for MAC table, MAC address, but somehow, for some reason, the port number is missing. So what do you do, right? So because so in Ethernet, what it does is quite simple. Because I don't know where to go, I send it to everyone, right? And in some implementations, you may just also send this packet back to yourself. This is also legal, okay? And somehow, in this example, so this is the simplest example I can come up with, but it's still quite a lot of details here. And let me try to walk through this. So now suppose you have 2 flows. So the server S1 is sending packets to server S3. And the black packet is also from S1, tries to send to S5 through the path, through this path. So it's basically T0, LA, and T1, and then to the servers. Okay. Now suppose this port is congested. So the black packets cannot be drained. And the purple packets is sending to S3. But S3 is dead, which means that the MAC table, the entry in the MAC table is gone. So what this switch does is try to send the purple packets to every port. But because this port is congested, this purple packet cannot be drained. But for those 2 ports, once they receive the packets, they will just drop the packets because those packets are not for them. But for port P3, because the black packet is ahead of the purple packet, right? So the purple packet actually cannot be drained. So if you have enough packets accumulated, so this P3 port will generate back pressure, the PF3 pulse frame, and the pulse frame actually can propagate, right? So in this case, you kind of will get something like that, right? Basically, the pulse frame is sending from here, and back to the source. It's like that. But now let's assume basically the server S4 is sending packets to S2. through this path, through the T1, LB, and the T0. So unfortunately, the server S2 is also dead. And the blue packet will be broadcast to everywhere, right, including this port, P2, right? And because this port got paused, so this blue packet cannot be drained. Then, in this case, you will form the back pressure like this. So now you got a problem. Is that you form a loop. All those pulse frames form a loop, and you got a deadlock. Okay, so this actually really happened in one of our test clusters. At that time, kind of 200 servers got stuck together, and nobody can move. It was quite a scary experience. And fortunately, it was just a test cluster.
Minimum spanning tree solve this problem?
No.
Doesn't.
It doesn't. It's because this actually is a kind of called a phasor interaction. So it's because the packet got the somehow the packet got a smart way by utilizing this multicasting protocol. It's supposed to travel down, but somehow it got a way to travel up. I think that's basically the root cause of this problem.
So if you prevent the broadcast to all ports, and
yeah, so I think that's our short-term solution. It's that basically, if I got a packet with up entry not complete, you just drop the packet. Actually, this can solve the problem. This is our short-term solution, right? And also the recommendation is that don't do flooding for lossless traffic. It's just too dangerous, right? And for a midterm solution, we got a paper. It's called a Tiger. It got rejected in SIGCOMM but published in Connext. I think it's a good paper actually. It's a good it has some good idea. So now suppose basically I think the part is that if you got a structure like that, you want to prevent the loop from forming, the circular dependency loop from forming. The idea actually is that, okay, now suppose you detect, now suppose this guy is supposed to go, the green guy, right? It's supposed to go down like this. But somehow it's not going down, it's going up. So this is a kind of something unusual. So if you detect that, what do? You switch this traffic to yet another lane. Right, and if you do this for the purple guy, right, you got this kind of figure, right? Then suppose all those kind of lanes are arranged in a kind of order so that they cannot form a loop. Then you kind of naturally break all the loops possible, right? Of course, this is just the high-level idea. But if you got an arbitrary network topology, this actually got quite complicated. I think this part is dealt in the paper. But the thing is that, okay, if you're just dealing with the file tree, you don't need that paper to deal with that. So basically, some intuition will help you solve the problem. Yeah. I think that's basically the Tiger paper is the midterm solution. Why I call it midterm? Right? I think basically longer-term solution is that, okay, just try to make RDMA work without the assumption that you have to use a lossless network. I think that will be better. The third problem we kind of deal with is, yep.
Is it provable?
Yeah.
So you prove that you will never have a.
Yeah, that's right. Actually, I think it's the idea is already there for quite a long time. I think our contribution there is basically to reduce the number of priorities that we need to keep the network free. I think that's part of our contribution. The third problem is called a post-frame storm. So now just to try to do a thought experiment. Okay, now suppose you have a bad guy. the 0 is a bad guy. So for some reason, it's just send out the pulse frame all the time, right? It should not do that, but anyway, it is doing this for no good reason. What will happen? So those pulse frames will propagate into the whole network. Of course, if you have a traffic to send, if you don't have a traffic to send, you are not worrying about that. But if you have traffic to send, you will really experience this kind of thing. So we were thinking this should be just a thought experiment, but it really happened. It happened several times. Didn't happen all the time, but it did happen, right? I think this is also a good reason why we don't like PFC, right? Because this PFC is kind of evil, right? So it can propagate, right? So all those kind of things that can propagate, can transfer, it's something we need to be very careful about. Well, the first one is called this slow receiver symptom. It's a kind of a little bit more than a bug. I think this probably is a conchoidal feature. So this is the setup, right? This is the NIC, the server, connected by PCIe, and this is a 40 gig link, and the PCIe is actually 64. So in some sense, is that okay? If you are receiving something from the Tor, you should not get any kind of bottleneck within the server system, because everything here is actually higher than 40 gigabits per second, right? So somehow you should not expect that your server is sending pulse frames to the switch, right? Because there's no good reason to do that, right? Because your system throughput is higher than the sender. In this case, is the Tor, right? But anyway, in this case, we receive in some cases we receive a lot of pulses from the NIC. We call it a slow receiver symptom. So what caused that? Actually, it's because this guy is sending pulse frame, so there must be some bottleneck here, right? It turned out that actually the bottleneck is the NIC. So the NIC was claimed be able to handle, I think it's 16 millions of Q pairs. Now a Q pair is a connection, but in reality, it does not have this many resources. So the number of connections it can handle in the NIC actually is roughly hundreds. It's 100. But if you have, so if it's run out of resources, so you can think about this guy is just a cache, a small cache of the whole data structure here, right? Once it's run out of the cache, it will stop and do a swap to ask the main data structure to get stuff there. So this actually causes, because it stops, and the packets actually processing got stuck, and then it will because it has to stop the packets from here. So it has to send out the pulse frame. This is why the pulse frame got generated.
In this one, you have too many Q pairs that are able to be stored in the NIC cache.
You can think like that, but the detail is a little bit more than that, because it actually does not have a concept of a Q pair. So this guy is a very limited resource constrained NIC. So I think the thing we need to be careful about this kind of design. I think this the same is true for all those kind of offloading techniques, right? When you are doing offloading, you probably are, because you cannot put all the resources that you have in the main data structure into this offloading device. So otherwise, you probably don't need to do offloading, right? So in that case, you are doing caching, right? And there will be cases that you will have a cache miss. And how to handle that I think in this case, I don't have a general principle to handle that. I think this probably is a case-by-case design choice that everyone will need to, to struggle with, right? Basically, this is because now people are saying, okay, now because the end of Moore's law, let's do offloading, or let's do this accelerated computing. Essentially, is that put to partition the functions into different places. Well, if you run, I think essentially those kind of things will happen again and again in the near future. Okay, I'll be very quick. So basically, I want to save some time to discuss what's next. So essentially, we put the stuff in production. We saw the latency reduction, and the throughput is also very good. We can achieve really very high throughput using, in this case, actually it's a 3-layer cloud network. But with the current design, that's a trade-off. You basically means that you cannot get low latency and high throughput at the same time. You can only get one. And, yeah, I think basically the lessons is, I think the biggest lesson is that, okay, here is that the providing a lossless network is really very hard. And if we can avoid doing that, we should. So what's next? Right. So so this is a very this kind of I use this kind of fulcrum for quite some time. The applications, architecture, protocol, and technology. So if you're familiar, this actually is the title of SIGCOMM. Right. So I would just let's go through some of this. The first one I think is I'm always asking people and asking myself is that okay, will software win again? So basically, from time to time, people will think, okay, now TCP is not good enough. Let's do offloading. This happened again and again, and probably will happen again. So this time, I'm saying that TCP is not good enough, right? Latency is not good, throughput is not good, right? So will someone be able to come up with a solution that, okay, software actually can handle 100 gig, can handle 200 gig, can reduce the latency to microsecond or microsecond level? I think there must be someone doing that. But sounds to me this time that story is really a kind of a little bit different. So if I need to bet, I will bet on hardware. Okay. It's because I saw when I did the experiment with this 100 gig, I saw how poor the performance of TCP is. So if I kind of want to bet, I kind of think that, okay, this time is really the time for RDMA. Or at least it's the time for hardware-based offloading. Well, I think this one is a kind of even bigger to me because it has a much bigger networking flavor. Is that do we really need a lossless network for RDMA? I think when I worked on RDMA, I really didn't got a choice. So the devices were already there in place. If we couldn't make RDMA work, it's a kind of loss of money. Right? But if I got a chance to do this project to start from scratch, I think it will be much better. We don't need to worry about this kind of deadlock stuff, right? And also but I think the challenge here is that, okay, how we can put this kind of transport protocol into the hardware. Yeah.
Do you think RDMA had all these problems because you evolved from an interconnect thing, like in the HPC world? Because this was like meant to be like an interconnect between multiple nodes, as it has all these memory semantics and everything.
Mm-hmm.
So do you think because it lacks all this fault tolerance stuff and all this reliability concerns, it was related to the interconnect?
Yeah, I think it came from there.
And now it's used as a network, and then
yeah. Now it's being used for distributed computing.
So do you think like Gen C, OpenCAPI, all these new guys, CCIX, for example, or Carrion CCPI, I think, will hit the same wall as RDMA because they have also memory semantics. They are also proposing interconnect. It's an interconnect protocol.
I think once they did do kind of distributed computing, they will hit a similar problem. Yeah. And I think it's a matter of scale.
Yeah.
If you just have several racks of stuff, you probably don't need to worry too much about that. Yeah. And you probably can do a centralized control.
And also flows.
Yeah, that's right. And if you are talking about the scale that I'm talking about, I think you will run into that kind of thing. Well, this is I think we once got a project for this. Is basically, well, if you want to have RDMA work for VM, you have SROV, right? And you should be able to make that work. But now, if you are using containers, it probably becomes much harder. Because now you may have tens of or hundreds of these VM containers, and there's no good way to do container-based virtualization for you, and at the same time still give you the performance of bare metal RDMA. I think this can be a still active research area. Okay, so this is something that currently I'm doing. It's basically it's RDMA for neural networks training. Right? Basically for us, for system networking guys, you can look at the training part. It's basically two parts. Well, forward propagation, backward propagation is computing. And then the gradients update, that's communication, computation and communication, right? And if you look at a little bit deeper, you kind of got this, right? You have an epoch composed of the mini batch. And if you look at each mini batch, you can have compute and communication, right? And of course, if communication is just a very minimal part of the whole big picture, it does not matter, right? So, but it turned out it's kind of not like that, right? If you look at this is a very simple setup. You have TensorFlow, you have 1PS, 2 workers, and running ResNet. And if you do millisecond level throughput measurement at the PS side, you kind of got this kind of figure. Right? Apparently it has a periodical pattern. And ResNet, for us, we know that its model is not very big. It's 200 to 300 megabytes, which means that if we are using a 100 gig network, that's around 30 milliseconds data communication. But if you look at that, actually it's more than that. This is 500 milliseconds. And the communication, apparently, sometimes it can be hundreds of milliseconds, right? And also, if you look at the throughput, it's just got 2 gigabytes per second. Right? I'm using a 100 gigabit per second network, which should be able to provide you 10 gigabytes per second throughput. So you are not using world bandwidth. Okay, now let's switch the networking to RDMA. So now certainly we got the sending rate actually increased quite a lot. Can be, in this case, the best case can come to 5 gigabytes per second. But somehow it's still not 10 gigabytes per second, right? So it sounds like there should be still some room. But the weird thing is that even if I use RDMA, so this is using the gRPC plus the GDR. So even if I'm using RDMA, we saw some kind of performance increase. Basically, the number of images that we can process in 1 second actually increased by 20 to 30%. But somehow it's not that big. So there must be something it's bottlenecked not by the networking, but by the system somewhere. And also, we kind of noticed that the receiving side of the PS is kind of bottlenecked just to 2 gigabit per second, for no good reason. Okay, we are kind of constructing a big GPU RDMA-based cluster in our in our data center. It will have thousands of the best GPUs and the very high bandwidth network. And I think, you know, if you guys are interested in working on this part, you know, basically, I think maybe we can discuss more. We can provide internship and also collaborations. So the last one I would like to discuss a little bit more. I think this is kind of quite important to make RDMA available to more programmers. Is actually RDMA is I think it's really very hard to program. Compared to TCP, I think everyone knows. Probably now nobody really writes socket-based piece of code anymore, right? Because you really don't need to do that. And maybe a lot of libraries, right? And also at the same time, people probably just move to HTTP. But if you really want to write a socket-based code, it's quite easy. But for RDMA, it's quite complicated, right? The IB verbs, you probably need 10 times of code, lines of code to just achieve the similar functionality. That is a kind of RSocket library. We basically try to provide the same program interface as a socket, but it's just except it's not a socket. Right? It does not have, for example, ePool for event handling. I think the biggest problem is probably not that the program itself. I think it's probably because of the way to abstract things in the HPC community is very different from us. So for example, for people like us, when we think about the abstraction, we think of everything as a file. Right? Everything is a file. Because if you think about how events are handled, it's through the ePool or pool. What kind of things you are pulling? You are pulling a file handler. Right? This is true for Windows. It's true for Linux. It's true for everything. But somehow, the RDMA queue pair and the CQ pair is similar to a socket. CQ is there's no equivalent comparison, but roughly you can think it's something like a completion queue in Windows. But they are not file handlers. So then this makes the whole programming very efficient because you don't have a common language to talk about, right? So this is so it's kind of invent everything, you know, by itself, and it's not good, right? And also, the programming environment for RDMA really sucks, right? If you try to write a piece of code for TCP/IP, you can always use your local host to do the communication, to do RPC. You are expecting once your development phase is ended, you split the code into client and server, it will just work, right? But for RDMA, if you don't have a real NIC inserted, it will not work. So you really there's no such kind of thing like a local host. Okay, and it's very hard to find some high quality piece of code for RDMA as well. Okay, so I think basically RDMA is a kind of experience in comeback in data center environment, especially for machine learning. That's really a good opportunity to make things good. And also, I think basically, if more people, especially the system networking people, work on RDMA, probably will have a chance to make it accessible to larger, bigger audience and to make it better technology. Eventually, maybe comparable to TCP/IP. for some time. Right. Yeah, so this is basically it's, for quite several years, I've been working on this. A lot of people contributed to this project. The majority part of this work was done when I was in Microsoft, and now I'm doing this RDMA for machine learning in my new company. Yeah. Okay. So I end here. Thank you.